All right, here we go. Good morning. We're going to look at kind of where we're at and what we can do with these things. We're at the point now where we can solve higher order polynomials. So first off, we're going to look at a definition of a polynomial, and then we're going to look at what we know about these things in the general. So if I have a polynomial, f of x, we have coefficients starting with the highest degree, working their way down to a constant, which is degree 0. Right? This would be x to the 0, but anything to the 0th is 1. And so this would be a constant. And so we have a collection of numbers that multiply powers of x's. N is integers, and they are positive. So we have no fractions, and we don't have x downstairs. We don't have any square roots, cube roots, or anything like that. We have n equals 0, 1, 2, 3, ... And these have made up our polynomials. Now, we early on looked at a constant function, linear functions, and quadratic functions. And what we found with the roots, the complete factored form, that this can be decomposed into linear components. And we're going to learn more about what happens if there's a nonlinear component, which is our friend the imaginary numbers coming back in. But I can make this out of a leading coefficient and a multiplication of factors with there being n factors. And these are nice because they're linear. If f of x equals 0, I can use the fact that any set of factors multiplied together would have to equal 0. And this is what we use to solve our factors. And so we now need to link these two ideas. That if I can decompose this into a set of linear factors, I can find the solutions. And what we mean by solutions are when the function equals 0, what are these factors? Or they'll get the nice name zeros or roots. I'm going to scroll up a bit here. One of our friends in this is the remainder theorem. Which says if I have a polynomial f of x and x minus k divides f of x, the remainder is f of k. And when x minus k is a factor of f of x, then f of k equals 0, because when we factor something, it doesn't leave behind a remainder. So this is where we have been. What we're going to do here is we're going to reverse this process for a bit. We're going to look at taking these things and going back up here. Just for a couple, so that we can see the utility of the backwards and forwards. So, let me see if I can get that here. I have a graph of a polynomial function here, and I want to find my equation for it. Well, there are some things I can say about it. It has 3 distinct roots or zeros, 2 turning points. So let me list this information down. I'll list it over here. So come back here. So we know we have zeros where x equals -2, 3, and 7. So these are my zeros, my roots, my solutions. Okay, these are the places where f of x equals 0. It crosses the x-axis. But what I want to find is f of x. Let's go back to the graph here. So I can say that this is most likely a 3rd degree polynomial. I just need one other point of data, and I think right here is looking nice. See right there? When x is 8, the function has a value of 10. And this would be a data point. And so I'm getting this from a graph, but I can say, hey, when I plug in 8 into this function, I get a value of 10. Well, we have enough information now that we can build our function. We'll come back up here. I'm going to scroll up. So when the function has a value of 8 equals 10, and we can build this function. So let's scroll up. And we can build it like this. The thing we don't know is the leading coefficient, but we now have all these linear factors. So let's put a form for our f of x. F of x is some leading coefficient. Well, let's turn these into factor form. So that's x plus 2 equals 0. X minus 3 equals 0. And x minus 7 equals 0. So I put in my factors. X plus 2, x minus 3, and x minus 7. And so we have the form that our polynomial function is going to have. We don't know the leading coefficient, but we have each of the linear factors. Well, let's find the leading coefficient. This is saying when x is 8, my answer is 10. So f of 8 equals 10. So 10 is going to equal a sub n, 8 plus 2, 8 times 8 minus 3, times 8 minus 7. So my a sub n is going to equal 10 times 5. And when x is 8, my answer is 10. So f of 8 equals 10. So 10 is going to equal a sub n, 8 plus 2, 8 times 8 minus 3, times 8 minus 7. So my a sub n is going to equal 10 times 5 times 1, or a sub n is going to equal 10 over 50, or 1/5. All right. So a little bit of work there, but we got this. And what I want to appreciate is if we know our roots, if we know where our solutions are, we're going to get the degree of the function. There's 3 x's. And we're going to get enough information that we can set up the form of the function. But to find the leading coefficient, we need at least one data point. And so this data point allows us to solve for the unknown leading coefficient. Well, let's put all of this back together. So my function has the form one-fifth x plus 2 times x minus 3 times x minus 7. And this is a workable way of using this. I think we might, if we wanted to, we could expand this out into polynomial form. So what do we have here? We have x squared minus 3x plus 2x, so minus x minus 6 times x minus 7, and then we'll multiply this through. So we get 1/5 x cubed minus x squared minus 6x minus 7x squared minus 7x minus plus 42. That's plus 7x. Sorry. All right, my x cubed, negative x squared, negative 6x, negative 7x squared, positive 7x, positive 42. And collecting like terms, I only have 1x cubed minus 8x squared plus x plus 42. And then I'll bring my 1/5 through. And we found our polynomial in polynomial form. This is what happens when you have data and you need to find a function. You now have something you can use in the future for something that has a solution of -2, 3, and 7 as your solutions that passes through the point of 8, 10. And it is really a byproduct of this completely factored form and solving for the leading coefficient. So all these roots have this information. They tell us how often the function is going to need to turn, what's going to happen if the function plunges across the x-axis or not. And in that, we have to kind of watch for some of our multiplicities and different values that can come up. So let's look at another way we can use this to our advantage here. All right, I'm going to look at the idea that we're going to write an equation. Let me put this over here. Yep. Let's go down. Write a polynomial function that has 0, 2 with a multiplicity of 2 and a 0 of -1. So we want to find the polynomial with a 0 of negative 2 and a multiplicity of 2. And a 0 of 1 with a multiplicity of 1. Now, what multiplicities told us were how often it touched that root, how often the root was repeated. And even multiplicities bounce. So this is going to end up being a power of 3 function. Our total multiplicities tell us the power of the function. So we have a multiplicity of 2 and a multiplicity of 1. So this is going to be an odd function. It's either going to come in from negative infinity and go out at positive infinity, or it's going to go in from positive infinity and go out to positive infinity. And we actually don't have the leading coefficient. So, but what we can tell is what our roots are. And so if I have a root of negative 2, that says x equals negative 2, so my linear factor is x plus 2. And if I have a root of 1, then my linear factor is x minus 1. So the polynomial I'm looking at, f of x, in its general form is going to have a leading coefficient, x plus 2, but this has a multiplicity of 2, so it gets to the second power. And so an x minus 1 has a multiplicity of 1, so it stays to the first power. So all of these things are coming together to help us define our functions. And so let's see, it's going to cross at a negative 2, and if it were to come, I'm going to use 2 different colors here. If it were to come, if a sub n was negative, it would come down to negative 2, bounce off, have some turning point, and leave at 1. So that was if a sub n is negative. If a sub n is positive, it would come up to negative 2, and it would kind of mirror that. And so that's the power of the leading coefficient in this. This is where our multiplicities come together. So we're looking at these things kind of backwards on how we develop them, because what we want to do is we want to be able to start here and reverse this process to find answers. We want to go backwards. We want to start with our polynomial, and we want to know all the answers we can see. So I want to have an idea of where these parts are built from and what they can come through. Now, throughout this chapter, I keep emphasizing the 2 important parts of a polynomial. So again, I'll go back to my general form of my polynomial here. The leading coefficient is getting pulled out to the front. And a sub 0 helps tell us what's going on in the middle. In fact, if I were to look at our quadratics that we had done before, this is, if I'm multiplying this out, I get x squared minus x minus 6. This minus 6 hints at my roots, because when we were factoring, when we were solving quadratics, we looked at all of the factors of 6 to find these. In fact, when we did the AC method, we looked at the leading coefficient and the constant to find the factors. And that actually holds through all polynomials. When I multiply more and more numbers, that trailing coefficient is related to the roots that came through it. So let me just make polynomial here. And so my roots are 4, -1, or I'm sorry, -4, +1, and -3, right? They get the opposite sign. Remember, our factor is in the form x minus k, so my roots are the opposite sign of my factors. But let me FOIL this out, and we want to look at the trailing coefficient. Now, I haven't put anything in A sub n yet. We'll deal with A sub n. I'm really focused on why this constant is important. Right? I've tried to point it out at least every lecture. That constant thing's important. And so let's look at why. So I'm going to FOIL the first two terms. X squared minus x plus 4x, that's plus 3x, minus 4. And now I'll multiply it by the last term. So x goes through each term here. X cubed plus 3x squared minus 4x as x goes through each term. And then multiply 3 through each term, plus 3x squared plus 9x minus 12. I'm going to collect like terms. So x cubed, 3x and 3x is plus 6x squared. -4, 9 is positive 5x minus 12. Well, what are my possible factors of 12? Well, 12 has factors of plus or minus 1 times plus or minus 12, plus or minus 2 times plus or minus 6, plus or minus 3 times plus or minus 4. And notice, there's the 3, there's the 4, and there's the 1. That constant trailing at the end contains information about every factor that went through it. It's just as the degree of the polynomial gets higher and higher, you're not looking at a pair of factors like you were with the quadratic, because the quadratic only had degree 2. There were only 2 factors to worry about when finding a solution. With higher order polynomials, you have an increasingly exponential amount of factors that you need to work your way through. And so we're going to use, to get us to our solution, a combination of the remainder theorem, a combination of division, and something we're going to call the rational zero test. Now, this will only find us the zeros if they are integers or rational numbers. They need to be a fraction, or they need to be an integer. If they're real numbers, we're going to have to use some other tricks to deduce what they are. But they can help us simplify what we have. So let's look at our rational zero test, and this will help us find this. It is taking this trailing constant and this leading coefficient. Notice, again, I'm going to scroll up quickly here. In this form, we have factored the leading coefficient out. That means every one of these numbers had this pulled out of it as a possible factor. Well, when we factor something out, we divide. And so this whole test is based on dividing that leading coefficient out and focusing on the constant. So I will give it to you in book speak right now. And this is the rational zero test. And for the rational zero test, it says, hey, let f of x equal, and it's going to be a polynomial. So we get our form back. Where a sub n doesn't equal 0. In other words, it has a constant here. If a sub n were 0, we would look at the next term and we rewrite this as a sub n, and we would shift. We'd be a lower degree polynomial. And so where a sub n equals 0, so this will represent a polynomial. With integer coefficients. So that means a sub n exists within integers, is an element of integers. A sub n minus 1 is an element of integers. And that means it's -1, 0, 1, ... to infinity. No fractions. If you get polynomials that have fractions or real numbers in them, what we do is we usually divide them into integers or multiply them in integers. And I'll show you that once we start using them. And the book says if PQ is a rational number written in lowest forms, and this is on page 306 in the book. Again, I'm going to use the book speak, but then we're going to use it. And if P over Q is a 0 of the function f of x, then P is a factor of the constant, which we call a sub 0. And Q is a factor of the leading coefficient. A sub n. And so what this says is if I have some number that is a 0 of the function, and it's an integer, or it's a rational number, then its numerator is related to the factors of the constant, and its denominator is related to the factors of the leading coefficient. So how do we use this? Well, what we can do is we want to find all possible rational PQs for a sub n and a sub 0. Right? We're going to find all of them because we know if one of them is a root, it works backwards. The problem is there are more possibilities than there are correct answers. So let's look at a particular function. We're going to look at f of x equals 6x cubed minus 5x squared minus 7x plus 4. So this upstairs, so I'm going to do a little jumping back and forth. This is what we're going to focus on. but this says that P is a factor of the constant term and Q is a factor of the leading coefficient. So my constant term, 4, makes up P. I'll write these. What colors do the book use? Book uses blues for P's, so I'll try to repeat that. So P is possibly going to be made up of the factors of 4. Well, 4 can be 1 times 4 or 2 times itself. But it's a positive 4, so I could have negative 1 times negative 4, I could have negative 2 times negative 2, or I could have the positives. So the possible factors I get for 4 are 1, 2, and 4 with their plus and minuses. I don't know the sign, and actually there's very little information telling me the sign right now. We'll find more sign information as we continue on. All right, and the book uses red for Q, so I'll use red for Q. Q gets determined by the factors of the leading coefficient, A sub 0. A sub n, sorry. And again, we're going to get the plus and minuses, so we always get plus and minus 1 hanging out there. And what else is 6 factored into? 2 and 3. And then the 1 is being times the 6 itself. So those are all of the possible factors of P and Q. All right, well, what are our roots? Well, our roots are the possibilities of P over Q. Well, I have many different options. So I have to write a list. What I usually do is I put my equal sign and I focus on one Q at a time. So I look at the 1 and I go, okay, I can have 1 on the denominator and I can have 1 on the numerator. And it's plus or minus for both, so this gets plus or minus. Now I'm just going to keep these in fraction forms for right now. We'll simplify this in a second. All right, so that's 1 for that. Notice that I can also still have 1 on the denominator, and I can have 2 on the numerator. So I get 2 over 1. It's still a plus or minus. And I can still have 1 on the denominator, and I can get 4 on the numerator. And I have exhausted all the possibilities with 1 on the denominator. So each one of these has to be a denominator for each one of these. So I end up with 12 possibilities, though some of them might cancel out. So I just work my way through each denominator. So now I have 2 on the denominator, and I can have 1 on the numerator with a plus or minus in the front. Plus or minuses are the norm here. We're either going to get the positive or negative value of it. So we end up having 24 possible roots to this 3rd degree polynomial. And that's only because the coefficients are fairly small. So this test doesn't narrow in right away. It gives you possibilities, but it's better than anything we had before. All right? Looking at this and trying to factor it down, we had no kind of anchor pin. Now we have an anchor pin where we can try to find all the possible rational roots. So what's the other one we have here? So I'm looking at 2 over 2, and then 4 over 2. continue on down on the next line here. So now I'm going to have 3 in my denominator. I'm going to look at my options with 3 in the denominator. Well, I know I already am going to have 3 of them, so I'll just write them out here. With 1, 2, and 4 in the numerator. 1, 2, and 4. And I guess this is, now that I think about it, I remember doing this in school when I was a wee little lad, you know, looking like the Lucky Charms guy. No one ever dressed me in a green suit. And we had to do this. We didn't have calculators. And so this was a painful experience, but it was the best tool we had. With calculators, this goes fairly quickly. And I've actually noticed that as I've watched people coming through with like different levels of high school algebra, they use the kind of check and guess, which I think came about from many multiple choice questions, where they plug numbers into a function to see what the answers was. Well, this works wonderful with that. If you have a calculator and you can set up a pattern of entering your function into the calculator, you can go through this list really, really quickly. All right, and my last ones will have 6 in the denominator, and so that's 1 over 6, 2 over 6, and 3 over 6. So each one of these is a denominator with each one of those over top of each of them. So you see the 1, 2, 4, 1, 2, 4, 1, 2, 4, 1, 2, 4, and the 1, 2, 3, 6 on the bottom. And they all get a plus or minus. Well, we can simplify these. So let's start simplifying these. So I'm going to come down. That's plus or minus 1. This is plus or minus 2. This is plus or minus 4. This one is plus or minus 1/2. This one is plus or minus 1, but we already have that. This one is plus or minus 2, which we already have. Now the thirds we don't have, so we get plus or minus 1/3, plus or minus 2/3, plus or minus 4/3. And then we get plus or minus 1/6. This becomes 1/3, which we already have. And this becomes 1/2, which we already have. And so when we simplify our fractions, we have 1, 2, 3, 4, 5, 6, 7, 8 possibilities. Well, with the plus or minus 16 possibilities. So we went from 24 down to 16. We've cleared out 8 of them by simplifying our fractions. But again, we are somewhere now. And so what we want to do is find one of them that's a root. One of them that's a root. One of them that's a part of a factor. One of them where if I put it in the function, the remainder is 0. So we take this list of numbers and we take our function. I'm going to rewrite the function down here and I'm going to scroll this up. And yes, these things do take a bit of paper space. You are right, the 3/6 should be a 4/6. Thank you, Billy. That's a 4/6. That simplifies to a 2/3. I'm typing back to Billy. Billy said, hey, that 3/6 should be a 4/6. It is. I'm going to correct it there. And I wish I could say I was, testing to see if you're awake. Maybe I'm just testing to see if I was awake. We lucked out, though. That mistake in its own right was still canceled out because this 2/3 cancels out with this. It's a repetition of this one. Whew. All right. Whew. So we need to test these. Now, one of the things I used to do, and I used to write these in order. So I would have written the 1/3, the 1/2, the 1/6, the 1/3, the 1/2, the 2/3, the the 4/3, the 2, and the 4. And I used to take them through in order. I don't always think that's helpful. So what I'm going to do here is I'm going to bring this back down. So 6x cubed minus 5x minus 7x. I'm going to put this underneath the list of the factors we have found, or the possible roots we have found. So f of x equals 6x cubed minus 5x squared. 6x cubed minus 5x squared minus 7x plus 4. And I am now going to drop these in one by one and see what will happen. Now, one of the things I want to notice here is if I just take my coefficients, negative 12 and positive 10. So positive 1's not going to work, but I'll show you this coming out. I'm going to keep in purple for here, so I want to drop in the positive 1. Well, anything a positive 1 gives me my coefficients back. That's why I like 1s. And you always get a positive 1 and a negative 1, so it's usually a good first test. So 6 minus 5 is 1. 1 minus 7 is negative 6. Negative 6 plus 4 is negative 2. So this is not a root because the remainder isn't 0. This was our remainder because we're using the remainder theorem. So the next one I'm going to plug in is negative 1. Now here, all the odd powers, negative 1 cubed is negative 1, so that turns that to a negative 6. Negative 1 squared is still positive 1, so that's still negative 5. Negative 1 times negative 7 is positive 7, and positive 4. And so that's negative 11, positive 11, this is 0. This is a root. So one of my factors, one factor is x plus 1, or x equals negative 1. Right, we want to start thinking that these are saying the same things, right, because we need to write either form. Now, this is a third degree polynomial. So I could go through and I could find my other 2 in here if they existed. But what I want to do, which I think might work better, is why don't I divide this by this? That'll give me a quadratic, and I already know what to do with quadratics. I can find my roots using the quadratic formula. I can find my other roots by factoring. So I'm going to do my division first. And I'm going to do it as a long division, or as a synthetic division. So 6, negative 5, negative 7.